Hello my friends, welcome to another Sign It video. In this one we're going to be looking at metallic bonding. We'll cover what bonds are, just briefly. We'll look at what metallic bonding is and why it has special properties, what the physical properties are, and then why it can conduct thermal energy and electricity. Let's go. We're just recapping here what bonds are. We've covered this in ionic and covalent bonds in separate videos. If you've had a look at those already, you'll be familiar. But with metallic bonding, it is still where atoms or ions are being stuck together. In this case, they're being held together still by electrostatic forces, and it's because of sharing electrons in this case. In metallic bonding, the electrons are being shared in a kind of delocalized space. Delocalized meaning not fixed to one location. They have a kind of shared area, if you like, of electrons. We'll look at that in just a second. So first we've got to say that metals in metallic bonding, it's just metals that are bonded together. There's no non-metals involved unless we're distorting the structure, making alloys, which we'll look at a little bit later. But metals here consist of giant structures. So we've seen giant structures in ionic and covalent bonding. This is the same. These are generally giant structures, lots of metal atoms put together, and they end up being in a regular pattern. And when they are in this regular pattern close together, what they end up doing is they share electrons from their outer shell, and they end up becoming delocalized. So these electrons end up coming into what we call an area of a sea of delocalized electrons. We can call it a sea, we can call it an area, we could say that these electrons are free electrons, or you could say the key word here, which is they are delocalized, which I think is the best one. Delocalized meaning they're no longer local to an area, they're in this shared space in between other metal ions. And what this means is that the atoms, or the nucleus part, becomes positive because they've given away electrons, they've become positive. And what we then have is the sea of negativity. The area where the electrons are moving freely, they're delocalized, that whole area ends up being negative. The electrons are free to move. They can move through that whole structure, which is why they can conduct electricity, because the electrons, the charge, can move. And it also ends up giving them very strong metallic bonds. So metals are really strong because of this structure. The positive charge of the nucleus of each of these, what are basically now ions, are attracted to the sea of negativity, and that holds everything together like glue, which is amazing. So it's a really cool kind of bonding. We don't need to be able to draw them specifically for different types of atoms like you have done for ionic and covalent bond, but you do need to be able to draw a representation and describe a representation of what a metallic bond is, like this. Because metals have these strong bonds, because the bonds being strong, metals have a high melting and a high boiling point. You know that because you know that to melt a metal you have to put in lots of energy, but it's because we're trying to break the intermolecular forces again. We're trying to separate out the different atoms from each other. We need to be able to move them freely from one another. And to do that we need to give lots of energy. So high energy, trying to break the intermolecular forces. And in pure metals, we find that atoms are arranged in layers. We said earlier they have a regular structure. So here we have one layer, two layers, three layers. Now, when you have layers like that, they're easy to be, these layers are easily moved past each other. So we could have this layer moving this way, this layer moving that way, and so on. And what those layers will do is as you bend a metal, you're actually moving these layers past each other. And that causes the metal to be bent. The actual metal itself is strong, but it can be bent, it can be shaped. Another word that we might use is malleable, but bent and shaped in this case is fine. And that's a property that we also saw a little bit of in graphite, that graphite's found in layers, that the layers will slide past each other, which is why we can use it in pencils. But graphite is quite brittle. Metals are very hard. They're really hard and tough to be broken, but they can be bent and shaped. But pure metals generally, because of this, are too soft for many uses. So what we try and do is make them a bit harder, a bit tougher still, by adding in other metals, or sometimes in the case of making steel, things like carbon. And this addition, making of a mixture, rather than just what was an element, a pure form of it, we're adding in different shaped atoms, and it disrupts the layers that we found before. So the disruption of the layers means that these layers can no longer be kind of easily found and no longer move freely past each other or as easily past each other as we did before. So it makes them much tougher to bend and shape and to break or mark. And so that's what we tend to do. We tend to make alloys which are more useful. The final properties that we're looking at for metals are conduction, which are quite unique here for metals because for ionic and most covalent substances they can't conduct electricity and they aren't generally very good conductors. However, for metals they are, and it's because they have these delocalized electrons, and both for heat and for electricity it's because of these electrons that gives them the conductive properties. So metals can conduct electricity because they have these delocalized electrons, these electrons that can move, and because they can move they can carry charge. So if we put a positive electrode and a negative electrode around this metal, we'd have the electrons moving in generally the direction of the positive electrode. And we have therefore a flow of charge from the negative end to the positive end. And that's current. So that's what electrical charge moving is. It's creating current, which is electricity. So that's a brilliant property of metals. And remember that graphite and graphene also have areas of delocalized electrons that can also then move and therefore conduct electricity. But they're also good conductors of thermal energy because, again, the energy is being transferred by these delocalized electrons, so they can move and they can carry this energy. So as they're moving around in the metal, they can carry that energy too, and that causes a quick transfer of energy from one end to the other. So they're very good conductors of thermal energy or heat. But that's it for metallic bonding. That's what we need to know. If you've got any questions or queries, do comment, do like and subscribe, and check out notifications for future videos too.